Okay, so more on exponential equations, compound interest, and half-life. So compound interest is governed by this formula. I'll explain it here in just a sec. P represents, and this is sometimes used as A, but P represents the principal or the amount of money you have. P sub 0 is your initial investment. R represents the APR, or the annual percentage rate. You may have seen this in car commercials most prominently, but APR is a pretty common term. It literally stands for annual percentage rate, how much you're getting per annum or year, okay? And then N would be the compounding interval. And that is literally number of times interest is added per year. Now, it turns out that, and so that if you notice, that, and by the way, T, we might as well explain that. T is the time in years. That is kind of important. It's indefinitely in years. So for this particular thing, now sometimes they're going to use A for amount or A naught, but all, for initial amount, right? But that's kind of academic. Those are just letters. The key thing here is we're talking about this part here. Now R, that annual percentage rate, as a decimal. So if you were talking about that annual percentage rate of 3%, then it would be 0.03, right? And that's actually about it. Now when we talk about compounding interval, this is how compound interest works. Under normal simple interest, they call it, simple interest. So you're going to get some economics whether you want it or not. Simple interest is we add a percent every year, right? So simple interest means that we're adding a certain percent. So if you're getting 3%, that means at the end of the year you get 3%, and that's it. Whereas compound interest, now compound like a compound sentence, right? Or compound word is made up of several words. A compound interest is made up of several different interests. So that means add percent every, well, there's several different ways to do it. You could add interest every, if you're really lucky, well, most of the time with banks you could talk about what is called quarterly, aka every 3 months. You could add it monthly, unlikely if you're talking about adding percentage, right? You could add it daily is another way that happens. And then you could also add it continuously. Now if you add it continuously, this is also known as continuous compound interest. This is where you'd use the P equals P naught e to the RT equation. Notice the continuously, right? Now, daily means you're adding the interest 365 times a year. Monthly means you're adding it every month or 12 times a year. And quarterly, which is every 3 months, means you're adding it 4 times every year. So in this case, for compound interest, when you're looking at the compounding interval, right, number of times interest added, this would mean that N is equal to 4, N is equal to 12, N is equal to 365. And we don't worry about this for continuously because it's kind of its own separate category because it's governed by this other equation, this E thing. Now we're going to look at how E came about here actually too. And we'll discover that as we add this interest more and more frequently, we get closer and closer to E. All right? I'll do an example to show that. So if you're looking at this equation, it does R over N here. So if you're talking about 4%, let's say annually compounded quarterly, that would mean 4%, 0.04 divided by 4. They don't pay you 4% for an annual percentage rate. They don't give you that every 3 months. That wouldn't make sense. What they do is they cut the interest up, right? They divide the interest up evenly over that period, okay? Let's take a look at some examples. It'll make a little bit more sense if we do that. So let's say that we were investing our initial amount of $100, right? And we are compounding, so let's go with our compounding. Let's run through let's go with quarterly, monthly, daily, and then continuously. And let's make our APR, just for argument's sake, let's go with 4%, okay? That means every year you'd get 4%. So if it was actually compounded yearly, that is, if we're talking simple interest, so simple interest, our equation is easy. The principal would equal the initial 100 times 1 plus, well, if we're talking about simple interest, then we're just adding the 4% every year, so we wouldn't even have to fool with the compounding interest formula. We just multiply by 1.04, remember 100% plus 4% is 104, to the t. And remember, t is always in years. That's kind of important. T is always in years. So that'd be simple interest. Quarterly. Quarterly would mean that it's every 3 months, which means we're adding interest 4 times per year. Here we're adding it 12, here we're adding it 365, and here we're adding it all the time, but we'll do that a little bit later. So when we're talking quarterly, there we go, that's better, not perfect. P equals 100 times, well, if we just run the formula, 1 plus 0.04 divided by 4 to the 4t. Now here's the explanation. 1 plus 0.04 to the 4. Well, 0.04 to the 4 is easy to simplify. That's 0.01. 1 plus 0.01. Now if you think about it, if we split the 4% evenly, and we're doing it 4 times a year, 4 split 4 ways is 1. So we're adding 1% every 3 months. Now, because t is in years, we need to add that interest how many times? Well, by the time we plug t equals 1 in here, we need to have added that 1% 4 times, meaning we're adding 1% 4 times in that 1 year, which means we're multiplying by 1.01, not once, not twice, not 3 times, but 4 times in the course of 1 year. So that's why we're multiplying the exponent. This causes this to repeat. Remember, t is always in years here, okay? So that would be our equation, right? And that would mean we'd be multiplying by 1.01 to the 4th. So if you wanted to simplify this, you could do let's do this more easily. We could do 1.01 to the 4th, which is 100 times 1.040604. Okay, 0.1. I'm actually going to type out, so what I've done here is, because I can separate this, 1.01 to the 4 is that, okay? So am I actually gaining a little bit more than 4%? Yes, because I'm adding 1%. Now if you think about it, if I add 1%, I increase the amount. If I take 1% of that, I'm getting a little bit more than 1% of my original. So the effect is, if I'm compounding quarterly, I'm getting a little bit better, not much bit, but a little bit better than just what the simple interest or APR thing would be, the annual percentage rate. This keeps going. So if we do monthly, then that would look like, so monthly, that would look like P equals 100 times 1 plus 0.04 still, that's still the APR, but over 12 this time to the 12t, okay? So what this means is I would be looking at 100 times, well, 0.04 divided by 12, so 0.04 divided by 12. So this works out to be right around 1.003333. It's actually repeating, right, to the 12t, which works out to be, so what happens is I'm not getting my 1%, right? well, I'm getting less than that. I'm getting 4/12, or 1/3 of that percent, so 1/3 of a percent each time. But when I take that 1 plus 0.04 divided by 12, right? And I raise it to the 12th power, I get 1.04074115. We'll go 4 to the t. So the idea is, if I add interest 12 times, even though I'm adding less interest each time, if I'm adding it 12 times, that is, I'm cutting up how often I'm adding it, I'm adding interest more frequently during that course that year, my effective rate is even better. It's a little bit better than it was if it was quarterly. There's not a lot of difference there, but it's certainly better. Now, if we add it daily, the same thing happens, except the numbers get even messier, because now I'm taking 100 plus 1 plus 0.04, but now I'm taking my 4% and I'm splitting it 365 ways. This, by the way, is how your credit card company charges you interest. So when you're running a credit card debt, it actually does it on a daily percentage rate, which is advantageous to them because you're actually getting they're getting a slightly better percentage rate. So I'm not going to bother with this minimum calculation, but I'm going to figure out what 1 plus 0.04 divided by 365 is, and then raise that to 365 power and see how much better that is, or, well, how much better that is than just simple interest or any of the other compoundings. So I would be doing 1 plus 0.04 divided by 365, and then I'd raise that, because I'm adding it once every day, right, to the 365th power. I get 1.04080849 to the t. So what does this mean? If I add interest daily, then I'm getting even better than a 4%, which would be my simple interest, right? Better than my quarterly, right? So as I add more interest more frequently, that is, compound it more frequently, then I get a slightly better than what my annual percentage rate is. Now, if I do this continuous, right? I apologize about the space. Then that would mean it'd be, believe it or not, it's actually simpler, e to the 0.04 t, which is 100 times. So now what I'm going to do is figure out what e to the 0.04 is, and you're going to see that, well, we'll find out. Let's see what we're going to see, right? E to the, 0.04 e to the, there we go, is 1 point, let me give myself a little bit more space here. 1.0408107 to the t. Now remember, in each of these cases, I can't mention this enough because I don't know what it is, but in each of these cases, these t's, right, are all in years. So if I plug in 1, it means after 1 year, 2 of 2 years, and so on, right? As I increase the compounding interval, what happens? Well, if I do it once, I get 4%. That makes sense. If I do it every 3 months, that is 4 times in 1 year, I get slightly better. Not much, but slightly better than 4%. If I add it every month, 12 times, right? Slightly better again. If I add it daily, slightly better. Still not a whole lot of difference. What happens if I add it continuously? Meaning I'm adding the interest over and over again, right? Kind of like a population growth type thing. Then I'm still getting slightly better than 4%, but not much better than daily, right? So you can kind of see that there's a limit to where we end up. So even when we end up continuous, we end up with this just a little bit better than 4%, okay? All right, half-life. Now, a substance, typically a radioactive substance, decays. What that means is it transmogrifies, okay, that's not actually correct, transmutes into something different. So if you had like uranium, right? Then it decays Typically, I believe it's beta and maybe some alpha particles, a little bit of gamma here and there. But in any event, we don't really care how it does. What it decays to some other substance, okay? Now, what this means is if I have my uranium, so let's say I had a lump of uranium, and I waited for its half-life, right? 1 half-life. Now, wow, that didn't work well, did it? 1 half-life. We'll talk about what exactly that means. That would mean that I would have half of my original uranium, and I would have the other half having changed into something else. So often we frame this, right? So this is uranium. Uranium. This is half the original. And well, this is the whole original, right? Uranium. Okay. When we talk about a half-life, this is a amount of time. Amount of time that it would take for half of this stuff to go away. Now, this A equals A naught, A for amount, right? So A would be the amount. A naught would be, you get it, probably guess this, the initial amount. Half is just the base. T is the time. Could be seconds, could be minutes, could be years, could be days, whatever. It depends on the situation. And then there's K, which is the half-life. That is the amount of time it takes. So what happens is, after a certain amount of time, we're going to have half the amount of uranium left that we had, which is why we're multiplying by 1/2. This is convenient because we can set this up very easily. So let's go with something that we actually know. Let's go with let's just make something up. How's that sound? Let's say we have something that has a 40-day half-life. Now, a couple things just happened here. It tells us that T is going to be in days, first off, and it means it takes 40 days for there to be half of it left. So let's say we had 100 grams to start. This means we could set up an equation for the amount that we've got of whatever this stuff is, such that A naught is 100 grams. That's our A naught, right? This would be our, I believe I called it K. Yeah, K, right? And we know that T is in days, okay? That's important. How do we know? Because it says a 40-day. So times 1/2 to the T over 40. Now, what does this mean? This means if I were to plug T equals 40 in, I should end up with A equals 50 grams. How do I know this? Because after 40 days, I would expect half of it to have changed into something else. Well, when we plug this into the equation, you can maybe see why we end up dividing by 40, because when I put a 40 in, divided by 40, that's the same as 1/2 to the first power, right? So if you think about it, dividing by 40 causes it to delay when it actually multiplies by 1/2. Whereas before, when you were talking about the compound interest, we were multiplying to repeat it over and over again. That is, repeat it more than once for every that change in T. Here it takes many changes of T to finally get this 1/2 to kick in. Okay. Now it does mean that we could figure out after T equals, say, 5 days, how much we actually have left. How? Well, we just plug 5 in. This is days, right? K equals 100 times 1/2 to the 5 over 40, and that would be a number, right? Now, if someone got tricky on you, right, then maybe they say, well, what happens after 1 year? By the way, you'd have to convert. That's 365 days, right? So you just say 100 times 1/2 to the 365 over 40. Now, you would expect there to be less than half. In fact, how many times does 40 go into 365? 9 times, right? A little bit more. Which means you'd expect this to get multiplied by 1/2 9 times plus right? So there'd be very little left after that amount of time, okay? So that would be how we'd model exponential decay. Now, one other side note, it turns out that when we're talking about this half-life is a continuous change. So when we're given a half-life, like let's say we have a half-life, so A equals A naught. Let's say we say that the half-life is equal to K, right? So T over K, right? Let's say it's years, right? It's a continuous change, which means this substance doesn't all change at once, just like a population wouldn't, which means that you could think of this in terms of a continuous change, where then you'd have this. I'm going to use R again because R and K are two different values. Everything else here, that is, this T and this T are the same thing. A naught and A naught, same thing. A and A, same thing. The only difference is that this e to the R is equal to, now when we're looking at 1/2 to the T over K, that's the same as 1/2 to the 1 over K to the T. That would mean that that portion of that, right, is equal to e to the R, okay? So this would be the continuous percent change of the substance, whereas this would be the half-life, that is the time that it takes for half of it to change, okay? The reason that we use this base 1/2 equation is because often half-lives are listed as a half-life. And the half-life is this many days, this many minutes, this many seconds, whatever it may be, okay? But it can be likened to a continuous change in this manner, okay? And that's it for half-life and compound interest.